So now let's look at the input control file, input.txt, right? So the only thing that you need to change, I need to change was first of all the title of the project, right? And then px and py, right? The number of processors in the x and y direction. So it's a two-dimensional program, and then the domain, the spatial domain is going to be two-dimensional, and then you have to actually create a two-dimensional mesh, right? And then this two-dimensional mesh is going to be partitioned onto different processes, right? So here I have 16 processes in the x dimension, right? And then 8 processes in the y dimension, right? So 16 times 8, that's 256, right? So for this particular simulation, I'm gonna need like 256. No, 128, right? It's 16 times 8, it's 128, right? Did I get it right? So 16 times 8, 128, right? So I got the multiplication wrong. So it's 108 processes, right? So usually you run one MPI process on one CPU core. So for this particular simulation, I'm gonna need like 128 CPU cores, right? And later on, I'm gonna talk about restrictions about the number of processes, right? Both in terms of the hardware, right, and then in terms of the simulation itself, right? So, but here we are going to need like 16 by 8, this many processes, 108 processes, right? And then the bathymetry information, right? Bathymetry information, which is provided by this particular file. I'll talk about how this file was actually generated. It was it's a text file, but you can download the bathymetry data from the internet, right? And then there are multiple sources of bathymetry data. One of the sources is some kind of geophysical kind of a data repository. Then you can actually download from that website, right? I forgot the name of the website, but it's easily Google can be found by Googling, right? So every line that starts with the exclamation mark is going to be kind of comment. So funwave is going to ignore those comment lines, right? Here I have like 3 lines that were commented out. I tried them, right, but it didn't actually make much of a difference for this particular simulation. But in other simulations, when you have a bathymetry that's kind of too rough, right, not smooth enough, you can actually use these kind of options or inputs to ask funwave to actually do the smoothing for you during the simulation, right? And then the result folder is going to be underneath the current directory, and then inside of this output folder. And then the bathymetry data is going to have a dimension. It's going to be a 2-dimensional kind of a matrix, right? So m globe is going to be the number of x coordinates, right? So in the x direction, which is longitude, right? Longitude, we're going to have 2,560 points, right? And then in the y direction, in our case, it's the latitude direction, right? We're going to have like 1,920 points, right? So in the x direction, in the longitude direction, we're going to have this many grid points, and then in the latitude direction, we're going to have this many points, right? And then the total simulation time, we're going to just run the simulation for 1800 seconds. That's about half an hour, and then we're going to generate this kind of a output. The output is also text file. So every 60 seconds, every minute, we're going to create a set of outputs for every minute, and then this line is comment out, and then this is for screen dump. So it's going to write out screen sort of kind of information about the time step every second, right? So this is 1 second. So this screen dump is going to be written into the, if you are submitting the jobs using PBS, a job scheduling system, usually this kind of screen dump is written into a output file for that particular job, right? Later on we can actually take a look at the output file. And then this is actually the longitude and latitude of the southwest point of your coordinate system, of your grid. So if you actually think about the entire simulation as being carried out in this kind of two-dimensional coordinate system, right? The southwest is going to be this point, right? The southwest point is going to be this point, and then that's going to be the origin. So once you have the origin, then you know where the two-dimensional grid is going to start, right? And then all you need is actually the interval, the grid interval in the two longitude and latitude directions, right? So in our case, the interval of the grid is this many degrees, right? So d theta, d phi is actually along the longitude direction, right? And then d theta is going to be along the latitude direction, right? And then what we need is the three input files for the initial conditions. So here we are going to initialize u, v, and z, right? Z is eta, that's the surface elevation of the water wave, right? And we are going to specify the initial condition externally, right? So this flag has to be true. And then in the following, we specify the input files for the three choices, the elevation of the water surface, and then the u velocity, and then the v velocity, the two velocities, the two horizontal velocities, right? And then they are going to be these kind of external text files, right? And then for this kind of simulation, you're going to need some kind of absorbing boundary conditions, because it's a wave that's going to propagate, right? And once it reaches the boundary of the grid, you don't want the wave to actually reflect back into the interior of the simulation domain. So you need some kind of a absorbing boundary condition. Here we are actually specifying the absorbing boundary condition as like 10 kilometers, right? The whole simulation domain is on the order of hundreds of meters. So if you have like hundreds of kilometers, right? So if you have like 10 kilometers or something as an absorbing boundary condition, it's still okay, right? Because most of the domain is still sort of in the interior. It's not on the boundary. And then I did not actually change the remaining inputs, but the remaining inputs are kind of a more or less kind of a fixed, right? I don't really have to change them to actually get some good results or reasonable results, right? Pretty much that's the entire input file. One of the things that I have to actually say is this number and then px and py, right? So the number px and py has to be divisible by m glob and n glob, right? So if you take 2560 divided by 16, it has to be divisible. 2005 divided by 16, you can get like 160, right? So that's the integer times, right? So if you do not specify the inputs as if you do not specify px or py as divisible as m glob and n glob, the simulation is gonna create some kind of problems, and at least on my cluster, it's gonna create it's not gonna run. It's gonna create a output that's telling you there's a problem inside of the MPI or wait or MPI wait or. Right, the source code is still inside of that parallel. If I close funwave-tvd version 3.6 SRC parallel, the problem still is from the same position. It's this particular line, right? So the reported error is going to tell you that the MPI wait all is going to have problems, right? But if you specify m glob and n glob to be multiples of px and py, integer multiples of px and py, then that problem is going to disappear. So you won't have that kind of problem. That's one of the pitfalls that I struggled with for like a really long time. Because when I was reading their user manual, they didn't actually specific. They talked about similar kind of problems for versions before 3.0. So I didn't actually expect to see this kind of problem for version 3.6, right? But it turns out if I do not actually satisfy this particular condition, I'm still gonna get an error message. So the code is not gonna run. So the code is gonna stop middle of the way. right, without actually doing any of the time stepping. And we're going to talk about how to generate those external input files in just a little bit. And another problem that's somehow kind of puzzling was that so here I have I'm using 128 CPU cores for my simulation. So if you look at my job script run.sh, here I'm actually requesting for just one node. So on my cluster, the actual every node is going to have like 128 CPU cores, right? So I just selected one node, and then I'm going to use all the cores, right? 128, and then for each of the core, I'm going to have like one MPI process. So MPI process is going to be 108, right? And then when I call MPI exec, the number of MPI processes is going to be 128, and then the processes per node is also 108, right? So basically, I'm just using one node and using all 108 cores on that one node, right? But why I didn't actually use two nodes, for example, right? If I use two nodes, then I have like 256 CPU cores, right? So all I have to do is to change this select to 2, right? And CPUs is going to be 256. No, and CPUs is still going to be 128 because this is the number of CPUs I'm going to use for every node per node, right? And then MPI process is going to be per node. Per node, MPI process is still going to be 128. But here I can actually specify 256, right? But why didn't I do that, right? But I actually tried that. But if I want to do that, all I have to do is to change the PY to 16 also. So 16 times 16, that's 256, right? So I can actually use two nodes, right? Each node has 128 cores. That's exactly 256 cores, right? So if I change PY to 16 using 256 cores on two nodes, then my simulation is gonna have problems. And the problems I'm gonna have, the problem that I have is this kind of problem. It's gonna create something like that, right? Again, this is something that I don't understand, right? And this is actually for an example with initial conditions all set to exactly 0, right? So there's no external excitation at all, right? So there's no source, there's no initial conditions. Initial condition is exactly 0, so no waves at all. So after you have finished a number of time steps, you are supposed to see exactly 0, right? No wave, no surface, no waves at all, right? You should be able to actually see exactly 0, but instead I see this kind of pattern, right? And then within each of the color blocks, the amplitude is extremely large, right? Very big amplitudes. And this kind of pattern, this kind of a wave pattern actually changes if I change the configuration of the configuration of my MPI processes in my job script. So if I do like 2 nodes, it's gonna give me this kind of thing, right? But if I change to 4 nodes, right? 4 nodes, and then with even more cores, then it's gonna change to a different pattern, right? So again, I don't really know what actually was going on. Maybe it's a problem with the code, right? But maybe it's something that's not set up correctly for the MPI on my cluster, right? I have no idea. But at this point, I don't really know. So if you see this kind of pattern, if you see this, it's possible. It's possible that this kind of a thing was created by the MPI. It's an MPI related problem. It's an MPI related. But as long as I'm just restrict my simulations to a single node, right? So this is 128 cores on a single node, right? There's no kind of a second node, right? As long as I restrict my entire simulation to just one node, right? All the cores on just one node, I don't see this kind of problem, right? This makes me wonder if it is indeed a MPI related problem or compiler related problem, right? Maybe the compiler is actually sort of implementing the MPI, or the MPI wrapper around the compiler has some kind of issue that I am not aware of, right? Yeah, so if I can use only just the one core or one node, then it limits the total number of processes I can actually utilize, right? It's only 128. That limits the. So if I can only just use if I have to actually restrict my simulation to just the one node, then it's gonna constrain my uh, the scale of the simulation that I can do. I cannot actually run simulations that's kind of too big, right? And then my simulation time is going to be like the amount of work clock time I'm going to need is going to be uh, quite long, right? Because I cannot actually scale to like lots of CPUs, right? So for this particular simulation, for this kind of grid, the grid is actually quite big already, right? It's for the examples in the simple case, for the examples in the simple cases that comes with the source code, most of the simulations are actually much smaller than this kind of a grid size, right? So the grid size that I'm using here is actually quite big compared to those examples that's in the simple cases, right? But still, this particular simulation took me about half an hour of work clock time on one node, 128 CPU cores, right, to run this particular simulation, up to half an hour, 1,800 seconds, right? Um, and um, yeah, that's everything that I want to say about this particular input file and all the pitfalls that I have encountered during my experiment with this particular code. Next, we are going to talk about how to create those inputs, how to create those uh, input files for the um, for the funwave TVD code.